In this video, we're going to work through the 2014 final exam manufacturing part. So, question 1.1. Which one of the following casting processes is suitable for casting complex parts accurately? So, sand casting was the most widely available one, or most widely used one, but the surfaces are quite rough due to the fact that we're using sand. Die casting can do parts very accurately, but they have to be quite simple in geometry so that the two mold halves can actually split open. Last wax casting is the one where the pattern is made from wax, then some or other refractory material is added around the outside and the wax is melted out, and then the molten metal is cast into the mold. So from these three first ones, best option so far is number C, last wax casting. Slush casting is used to do hollow components like lamps, pedestals and so forth, and the expanded polystyrene process is also basically a sand casting process, so also not very accurate. So the correct answer for 1.1 is C. Question 1.2 says, Figure 1 illustrates a manufactured component. The sheet metal strip is 3 mm thick and it has a shear strength of 380 megapascal. Which of the following manufacturing operations were used to produce this component? So this component is made from a sheet or a strip of metal, and it is cut around this side and around that side. And remember, we don't have to cut along this edge because this width over here is the same as that width over there. So we're literally only cutting that half circle and that half circle. So of the options we have available, we have A, drilling. Obviously this is not drilling. Drilling is a hole making operation which creates generally circular holes into the work part. Blanking, this is a metal shearing operation, so this could be. Centrifugal casting, no. Forging, no. Forging is when you heat a material to below its melting point and then use mechanical force to alter its shape. So this is not what's happening here. E, drawing. Drawing was when you take a sheet metal component and stretch it into a certain cylindrical shape to give a certain part. So also not drawing. The correct answer in this case is B, blanking. Question 1.3. Determine the force required to cut this part from the metal strip in figure 1. So the equation we are going to use is F equal to STL. S is my material shear strength. T is the thickness. L is the length of the cut. So not the total length, the length of where we are cutting. So the shear strength was given in question 1.2 as 380 megapascal. The material thickness was also given there as 3 millimeters. And now all we need to do is look at the picture to determine the length of the cut. So the length of the cut is basically this edge length over there added to that edge length over there. So those are two half circles, meaning the total length is just the perimeter of that circle with a diameter of 40 millimeters. So S is given as 380 times 10 to the 6 pascals times thickness of 3 millimeters, so I'm just converting it to meters, multiplied by the length of the cut, which is equal to 2 pi r, or pi times diameter, whichever one you want to use. So you'll note I wrote all of this in SI units. It's always the safest to work with meters and newtons instead of working with megapascals, because then your distance unit has to be in millimeters, which is going to cause you to make a mistake somewhere along the line. So if we multiply all of this out, we get 143.26 times 10 to the 3 Newton, so 143.26 kilonewton. That's option E. Question 1.4. Identify one of the machining operations that was performed to shape the part in figure 2. So this is the part in figure 2. It is a cylindrical component with the overall length of 60 plus 90, so overall length is 150. Initial diameter, or the big side, is 60, the small side is 40. It's got a slot through here and 2 holes there. So the machining operations to make something like this would, number one, be turning, to get the 60 diameter down to a 40. Over here we have milling to make that groove through there, and here for this one and that one we have drilling. So let's see what options we have available in the question. We have chamfering. So chamfering is when you take a sharp corner and you cut it off at 45 degrees to yield that kind of shape. So that is chamfering, so chamfering was not used. Milling was used. Slush casting, no. This slush casting process creates hollow components. That shaft was not shown to be hollow. Bending, no. Punching, no. Punching generally is applied to sheet stock. That was a solid bar, so punching cannot really be performed there. That means correct option is 1.4 B. Question 1.5. A round bar is to be machined to yield the part in figure 2. During the lathing operation, so lathing is turning, the diameter is reduced. Okay, that makes sense, we've already identified that. Calculate the feed rate required on the lathe to remove 509,000 cubic millimeters per minute if the chuck turns at 900 RPM. So we are given material removal rate is 509,000, and note the unit is in cubic millimeters. We're given our rotational speed is equal to 900 RPM. My big diameter was 60, so that's the one we use for our equation. So D is equal to 60. And now we can start calculating. So we have our material removal rate equation, which says MRR is equal to VFD. To be able to use this equation, we need to first get V and D. We're given material removal rate, so then we can calculate the feed. So V is equal to N times pi times our outside diameter, which is equal to 900 times pi times 60 times 10 to the minus 3 gives me 169.65 meters per minute. Now that we have V for this equation, we can quickly figure out what D is. We're going from a 60 down to a 40. So the difference between the two is 20, but there will be a D at the bottom and a D at the top because it is a turning operation, so small d is equal to 10. Now we can solve for my feed. So 509,000 is equal to 169.65 times F times 10. Now, some of you might have noticed that this is in meters. I must convert it to millimeters. I could have just used the millimeters in the top equation there. It doesn't really matter. Good, so cubic millimeters, 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 and this one is millimeters per revolution. So F then works out to 300 times 10 to the minus 3 millimeters per revolution. Then there was an equation. Our feed rate is equal to our rotational speed times our feed, which is 900 times so this one is revolutions per minute, this one is distance per revolution. So the revolutions cancel out, then we just have distance per minute, which is 270 millimeters per minute. Okay, let's have a look at our options. The options we have available is 203, 135, 405, 270. Good, so 1.5 answer is D. Question 1.6. In order to manufacture the slot 8 mm deep in the shaft of figure 2, a face milling operation is performed using a 4-tooth 15 mm diameter milling point. For the cutting conditions V equal to 25 meters per minute and our chip load F is equal to 0.1 millimeter per tooth. Determine the time for the milling operation. So, in milling, I would always recommend that you draw the picture. Here we have a circle with a diameter of 60. We have a milling cutter with a diameter of 15. It's got 4 teeth on it, and it now has to cut a groove through this part like that. And we are told that it is face milling. I'll get to that in a moment. So with calculating the distance that we need to travel this cutting tool, we basically need to determine the approach and over travel distances. So basically the width we have to travel with this part is 60, but the moment this edge makes contact over there, if we're now moving it in that direction, the moment those two make contact, it starts to cut, but it isn't at my 60 distance yet. Or basically, if this point touches there and I move it 60, that point will touch on that side. So we'll still have these little triangles that need to be cut off. So that's why we have an approach and an over travel distance in face milling. Remember the difference between face milling and peripheral milling? Face milling, as we move over, let's say the cutter is now somewhere over there, these back teeth are still making contact with the work part. They're not removing a lot of material, but they're all still touching the surface. So if I just move to where this point and that point cross each other, and I lift it up, then I'm going to have an inconsistent pattern on the surface in here, which is not good for surface quality. So that's why with face milling we have to progress all the way through. So there's my little cutter. Because we're making contact on the outside edge over there, it means my approach distance is equal to the radius of the cutter, which is 15 over 2. And on the other side, my over travel is also equal to 15 over 2. Okay, so the time equation, time is equal to L plus 2A over FR. So L is 60 in this case, A is equal to 7.5, but we still need to determine FR. FR is equal to N, rotational speed, times the number of teeth, times the chip load. And my rotational speed I need to determine with an equation similar to the previous problem. N is equal to V over pi d. So that's 25 over pi times the diameter of the cutter, 15. At the bottom the cutter diameter is given in millimeters, so at the top I must multiply by 1000 to get it to millimeters as well, times 4, this is my number of teeth, times the chip load 0,1, which was given in the question, which gives me a feed rate of 212.2 millimeters per minute. So that means time is equal to L plus 2A over FR, which is equal to 60 plus 2 times 15 over 2 divided by 212.2065. And that gives us an answer of 0.35343. Good, let's see if we have any of those options available. Okay, none of these options are less than 1, so somewhere I missed something. Okay, now our feed rate equation gives an answer in millimeters per minute. So basically this answer, if you cancel out the units, is in minutes. So I must just multiply that by 60 to give it as an answer in seconds. So times 60 is 21.2 seconds. So that would be option B. Question 1.7. After the milling operation, 2 holes are drilled using a 8 mm drill. Calculate the material removal rate for one of the holes, given the cutting conditions are V equal to 12 meters per minute and F equal to 0.25 millimeters per revolution. So material removal rate is what we want to determine. The diameter of the drill is 8 millimeters. Velocity is 12 meters per minute. And our feed is 0.25 millimeters per revolution. Material removal rate for drilling is pi over 4d squared FR. So we need to determine FR and then we can use this equation. FR is determined from the feed and the rotational speed. FR is N times F. And N we need to get from our velocity versus diameter ratio, which is V over pi d. Times F. So now we can start plugging values in. We have 12 meters at the top. I'm just going to multiply that by 1000 to get it to millimeters. Pi times 8, that is my diameter of the drill bit, times my feed, which was given as 0.25. So that gives me a feed rate of 119 point, sorry about that, a feed rate of 119.37 millimeters per minute. So now I can plug all of this into my material removal rate equation. So that gives me a material removal rate of about 6000 cubic millimeters per minute. Of the options available, 6000 is option A. Question 1.8. Tolerancing is crucial to the success of a manufactured part because it acts as an indication of the final aesthetics value of the product. No. Tolerances have nothing to do with aesthetics, they have to do with proper functioning. It specifies a range within which a dimension is allowed to vary in order to allow the part to function properly within an assembly. That sounds about right. Tolerancing is crucial to the success of a manufactured part because it will determine the type and quantity of nuts and bolts to use in the assembly. Nope. It allows the lowest cost of the product. No. Usually, tolerancing actually adds to the cost. So the correct answer in this case, 1.8b. Question 1.9. Identify the fit category illustrated in figure 3. So this is figure 3. We have a shaft and a hole, and you'll notice that this crossed out region indicates the allowable variance in sizes, so from the smallest to the biggest. So you'll notice that the biggest hole is still smaller than the smallest possible shaft. So this kind of fit, remember we get 3 types. First one is a clearance fit, then you have a transition fit. Clearance fit is when all of the shafts will fit into all of the holes. Transition fit is when some of the shafts will fit into some of the holes. And an interference fit is when none of the shafts will fit loosely into any of the holes. So basically what happens in this case is you will force it in by means of a hydraulic press, and that stretches this outside material around the shaft, which will give you a reasonably tight fit that causes them to not be able to move relative to each other. So, limiting, interference, transition, clearance or normal. 1.9b is a transitional fit. One point 10. Use figure 4 to determine the fit of a 45mm shaft with ISO standard H8F7. So to do the tolerance, we'll have to make use of the tolerance table, and in this case we have an H8F7. So if we go to this table, you'll see the H8F7 column is actually under clearance fits. So this is the column we are going to be using for this problem. The shaft has a diameter of 45mm. So this is the column. Now we need to find the row to work with. We've got over and to, so over 30 to 40, nope, over 40 to 50. Yes, so this row is the row we are going to use, and this column is the column we are going to use. So for the hole we have a 0 and a plus 39, and for the shaft we have a minus 25 and a minus 50. Remember, those values given there are in micrometers, so it is 50 times 10 to the minus 3 millimeters. Good, now we can do the calculations. So we are given 45mm diameter shaft. For the hole we have plus 0, plus 39. For the shaft we have minus 50, minus 25. Remember, micrometers. So the hole can vary. The smallest hole will be 45.000, and it can go up to a maximum of 45.039. And for the shaft, it is 45, and then we add this, which is a minus 50, so 44.950, and it can vary up to 44.975. So the shaft in this case is X and the hole is Y. So now we can go to our options and see which of them work. So we're looking for an X value of 44.95 to 44.975. Option A, X is 45, so no, it's not option A. B, 44.975 and 44.95 for my X value. So far that's good. For my Y value, we're going from 45.000 up to 45.039. So that's my Y value as well. Number C, a tolerance will not have just a single value, you need the band. So C is not possible and D is not possible. E, you'll notice we subtracted 0.25 and 0.5, but we're supposed to subtract 0.025. So this one, the tolerance was actually 10 times more severe than what it needed to be. So this one is also incorrect. Correct answer is B. So that is basically the summary of the 2014 final exam manufacturing side.